Okay, so up until now, we've done things like said, okay, there's this function, and it had a formula like maybe f of x equals x squared. And we said, okay, let's talk about the picture, the graph, which happened to be parabola. Well, actually, what we could do is we could actually introduce a new function just by describing a graph, right? So the graph below, so just the points that are drawn in blue, so not the axes just kind of tell us where everything is anchored, but the points that are drawn in blue forms a graph. And it happens to pass a vertical line test. Wherever you draw a vertical line, it either goes through one blue point or no blue points. You never can draw a vertical line that goes through multiple blue points. So this passes the vertical line test, and so it's the graph of a function. It's a function that's described using a picture instead of using a formula. So question, if the graph below describes the function f of x, find f of 3. Well, f of 3 is equal to 1. That's because the point 3, 1 right here, that's a point on the graph. And this is just exercising the thing that we just said a moment ago. Recall that the point a comma b is on the graph of f if and only if f of a is equal to b. So when we were asked f of 3, 3 right here is a. And so we're looking for a point where the x coordinate is 3, right? Because it says a comma b. So 3 comma something, and that's this point right here. And we get 1 as the y value. Okay, if the graph below describes the function f of x, then let's find f of 3 plus f of 5. All right, well, f of 3 is 1 due to this point. F of 5 is 2 due to this point. So you go in the graph and you look for a point where the x-coordinate is 5. And good thing there's only one point where the x-coordinate is 5 because of the vertical line test. And at that point, the y value is 2. So f of 3 is equal to 1. F of 5 is equal to 2, and now we can answer what f of 3 plus f of 5 is. So f of 3 plus f of 5 equals 1 plus 2, right? The f of 3 got replaced with a 1, the f of 5 got replaced with a 2, then we simplify 1 plus 2 to be 3. All right, let's try something a little more complicated. If the graph below describes the function f, and g is another function, so g is defined by formula, g of x is equal to x squared plus 5, let's find f of 3 plus g of 3. So the question here deals with two different functions. F is described by the graph, g is described by a formula. So f of 3 is equal to 4 due to this point right here in the picture. 3 comma 4 is a point on the graph. G of 3 is 3 squared plus 5. Okay, so f of 3 plus g of 3 is 4 plus, and then the value of g of 3 was 3 squared plus 5. We can simplify this to become 18. Okay, just as a side note, because we will be thinking about things like this a little more in the future, let's talk about what graphs of functions have to say about equations. So consider the equation x squared plus 3x equals 8 plus x. Now we have kind of all kinds of methods to solve an equation like this, but the point right now is not to solve. I'd like to instead say, you know what, let's take the left side, x squared plus 3x, and call that now the formula of a new function f. And the right side, 8 plus x, let's call that a new function, g of x. Then let's just see a picture of this using a graphing calculator. Here it is. So there's what was the left side, and then in purple is the right side. And we see that these two will intersect at two x values. And one of those is x equals -4, and the other of these is x is equal to 2. And so that's what we see here. From the picture, the graphs intersect at x equals -4 or x equals 2. Now, if you add 1 to both sides of the equation, to the equation up at the top, you're going to get x squared plus 3x plus 1 equals 8 plus x plus 1. Of course, we could have written that as 9 plus x. We'll just leave it like that. Then let's talk about the graph interpretation of adding 1 to both sides. So let's define a new function j, which is the new left side, x squared plus 3x plus 1, and then k of x will be 8 plus x plus 1. And if we go back to that same link and we look at the graph of j and k, let's see how they're related to f and g, and then we'll also see that the intersections are still at -4 and at 2. So here's j in black, and then there's k in red. So you'll notice that the intersection, let me zoom in here, the intersection of the black and red at x equals -4, and the intersection of the black and red here at x is equal to 2. So those still happen. But the other thing to really note here, perhaps turning these off will help, there's f and there's j. So this is just 1 unit higher. Similarly, here's g, and then here's k, which is drawn 1 unit higher. So it's just taking the pictures that we had here in green and purple. And if we raise each of these up by 1 unit, you'll get what's in black and red. And still, the x-coordinates of the intersections still happen to be at the same place. So applying the same action to both sides of an equation does not change the x values of the intersections, which is good because though the equation may look different, we get an equivalent problem, and the x values that are relevant will be the same. If you, in fact, go through the process of solving x squared plus 3x equals 8 plus x, you'll find that there are two solutions, and those two solutions will be x equals -4 or x equals 2.